When millions of gallons of turbulent water slam into a rigid concrete pillar, the water usually wins. In environments with extreme seasonal flooding, standard infrastructure designed to stand still will eventually shatter under the pressure. Look at the Shillong Plateau in northeast India. Towns here, like Mawsynram and Cherrapunji, receive rainfall measured in meters, not centimeters. The monsoon season turns ankle-deep streams into impassable, raging torrents. In this level of humidity and water volume, standard building materials deteriorate rapidly. Steel frameworks corrode within a few seasons, and wooden supports quickly rot away in the damp air. Engineering a structure to remain perfectly static in an environment that actively dissolves rigid materials is a losing battle. The local geography simply overpowers conventional construction. Now, global climate change is supercharging those extremes. The rapid retreat of Himalayan glaciers is actively breaking the historical water cycle the entire region relies on. This map shows agricultural drought conditions across the northeastern region during a recent summer. The widespread red and pink zones indicate severe and very severe drought. Paradoxically, the wettest place on Earth is now experiencing prolonged dry spells. This chart shows the region's monsoon rainfall distribution over a 27-year period. You can clearly see drastic spikes and dips starting around the year 2000. These chaotic shifts are wiping out conventional crops and costing millions of tons of food grain. When the environment violently oscillates between flash floods and complete dry spells, static systems fail. Whether it's a rigid concrete bridge or a strict planting schedule, structures that cannot bend will break. The Khasi and Jaintia peoples developed an alternative to static engineering. They cross these swollen rivers on Jingqing Dri, living root bridges. The construction process takes decades. Builders guide the long, flexible roots of the Ficus elastica across deep river gorges, feeding them through hollowed-out erica palm trunks to direct their growth toward the opposite bank. The core mechanism making this possible is a biological process called inosculation. When the cambium layers, the living, growing tissue just under the bark, of two independent roots are pressed together, they literally weld into a single living structural member, sharing the same internal growth ring. And here is how they react to human footsteps. The roots respond to mechanical load by increasing their secondary growth in the exact direction of the stress. As weight pushes down, the living tissue thickens and reinforces itself to bear that specific burden. Every step on a steel bridge inflicts microscopic damage that eventually leads to structural fatigue. Every step you take on a living root bridge actually stimulates it to grow stronger. The logic of moving with the environment defines survival across the entire regional ecosystem. This isn't just about bridges, it's about how every living system here handles the water. Kaziranga expects and requires 70 to 80% of its landmass to flood annually. Instead of fighting the water, the local wildlife simply adapts, migrating to elevated riverine islands known as chaporis until the waters recede. Local farmers are translating this adaptive logic to food security. To survive erratic rainfall, they use conservation techniques like zero tillage, leaving plant residue to shield the soil. This prevents moisture from evaporating during heat waves, mirroring the way root bridges use their own growth to protect against environmental stress. Biological resilience here depends entirely on moving with the water and adapting to the load, rather than trying to block it out with rigid barriers. The ultimate capability of this indigenous bioengineering is staggering. Near the town of Panersla, a massive root bridge spans over 52 meters. It required zero imported materials, produced no construction waste, and sequesters carbon while carrying daily foot traffic. Modern architects are now studying these spans to develop a field called biobotanic, or botanical building. The goal is to replicate this method and integrate living plants as load-bearing structural elements in urban environments. As the planet warms, extreme weather events like those in northeast India are appearing globally. Our current static infrastructure, the concrete networks our cities rely on, is highly vulnerable to these erratic shifts in temperature and water volume. Surviving a warmer, more chaotic world requires us to rethink how we build. We have to abandon rigid, static defenses in favor of engineering systems that can grow, bend, and adapt to the burdens they carry.